So we defined in a graph what is a walk, then a special walk is a path, and special path is a cycle. I hope these definitions are clear by now. So a walk between UV also implies that there is a path between UV. Idea is that in a walk, if vertices are repeated, then you can drop that part. Then you will get a path with no repetition of vertices. There was this lemma that if there is a walk with the same source and destination, then there is also a cycle in the graph. So you have to complete this proof. This may, in some examples, it may happen that the cycle is not from x0 to x0. Okay, cycle may be from something else. So you have to actually, the way you will prove it is when there is a long path, when there is a path which is at least 3, then in this case you can do an induction on the length of the path. Okay, you basically say that while walking from x0 to xk, if there is some other vertex which repeats, then you should focus on that. Okay, so that will be a shorter walk, and you can get by induction that there is a cycle. So those possibilities are also there. So you have to formally prove this by induction. And if the path is smaller than 3, then in this case, or the walk is smaller than 3, then we showed that there is a contradiction, this cannot happen. Okay, so somebody pointed out an example where it's a long walk, but still it's not x0 that gives a cycle, but something else. Then we defined connected graph, and we looked at matrix product. So adjacency matrix of the graph is A. What happens when you square it? Right, so we showed by this simple proof that when you square it, if u comma v entry is positive, not 0, then it means that there is a path from u to v of length 2. Right, this is what we had shown, and in general, for a to the k, you can say that the entry u comma v of a to the k will always give you a lower bound on the number of paths of length k. Yeah, so this is so one issue here was that we always assume that the graph is simple, which means there are no loops. If there are no self loops, then basically in the matrix the diagonal entries they're all 0, right? So so then there could be a problem in giving an exact count. But suppose we put on the diagonal entry all 1, which means we add the self loops. So in that case you can show that a raised to k's uvth entry gives you all the walks of that length k. Okay, this you can formally prove. Any questions till now? So a raised to k uv is positive due to the contributions like contributions by length k paths of the type. So you start with V0, that's u, then there is an edge from V0 to some other vertex V1, then from there to some other vertex V2 and so on till you reach Vk minus 1 and then Vk. Vk has to be Is that right? Yeah, it has to be. So for k equal to 1, V0 is u and yeah, V1 is V, right? So in the graph, what happens is from u to v, if you can walk this way, doesn't matter what these vertices vi's are, since we have also added self loops, they may also be consecutively same, v1 and v2 may be the same vertex. So everything is allowed as long as you can do this walk physically. This will actually contribute in the matrix power. Okay, and each such walk contributes exactly 1. This you can check. So each such walk contributes a 1 in a raised to k uvth entry. And hence you show that a raised to k uvth entry is exactly the number of walks of length k from source u and destination v. Is that clear? Yes. A u comma u1. Yes, so what happens if we don't fix? Say all these diagonal entries are 0, then what is the interpretation of a raised to k u comma v? It is the number of what? It is the number of walks or paths? One of the v can be what? Yeah, so the problem will be that you cannot say that it's the paths, and you also cannot say that it's all the walks. Well, because in a walk, aren't you allowed to have UU or VI? That was not clear, right? Was it that the definition we were not specific to that. See, walk we said is, I see we said xi plus 1 is in the edge. Okay. So with that, yeah, then xi and xi comma xi cannot come, and then probably you can say walk also. So what should we say? Number of walks? U to V of length. Is it exactly k or less than equal to k? Yes, so I guess this is also true. Yeah, with the understanding that these VIs will all be, I mean, they cannot repeat immediately. No consecutive VI plus 1 are equal. And third thing is, what about paths? In either of these cases, what can you say about number of paths? Yeah, so for paths, we don't seem to get an equality. We just get the first line that a raised to k u comma v will give you a lower bound. So if it is positive, then it means that there is a path. And even the path length, you don't get exactly k, right? It is less than equal to k. So maybe we should write that down. There is this, these qualifiers are needed. is less than equal to number of paths u to v of length less than equal to k. So only a lower bound and for the length upper bound. Okay, any questions till now? So then you understood powering of the matrix, and we'll start a new, sorry, the first inequality. Yeah, that is true. Yeah, but that is not very interesting. What I want to say is that this number of paths is at least 1 if e raised to k uv is non-zero. That also I want to say. So if the entry is positive, then there has to be a path. Is that clear? It can't be that there is no path. So path indication will be there. Same thing here. Any questions? Is less? Well, the value of a raised to k uv will be quite large because of the walks. And every walk gives some path, but one path may correspond to many walks. No, but every path is a walk. Path cannot exceed walk. That is true, but yeah, so that you prove then, because it's from u to v up to k. So basically, in that length, any path that you will see, it's also a walk of length k. It can be expanded into a walk. Any path of that much length extends to a proper walk of length k. So that can be shown, that's not hard. In fact, we have shown those things in the first, when we defined walk and path. So let's move on to trees now. This is important both in CS algo and graph theory. So what is a tree? You will see many kinds of trees in data structures and computer science. So here the most basic one is what we mean, which is it's a graph which is connected. So let me define this. So tree is a graph, is a connected graph. And the main property is it should not have a, it should be cycle free. So tree is a connected graph with no cycle. Okay, that's what a tree is. So can you give an example of a graph, of two graphs on 3 vertices? One is a tree, other is not. I should not know. So on 3 till, okay, now we can actually ask that question also. Yeah, same question. So example of two graphs. So of a tree and non-tree on n equal to 3. What is it? So yeah, triangle. So this is obviously C3, so this is not a tree. On the other hand, this is a tree. Can you give another non-isomorphic example of tree? No, on 3 vertices, a tree different from what I've drawn. Single line, right? This is isomorphic. So I guess there is no other tree then. This is isomorphic. So the another example of a graph which is on n equal to 3, not a tree, non-isomorphic to C3. Yes, so you can make it unconnected like this. Right, so first and the fourth, they are both graphs on 3 vertices, non-isomorphic, non-trees. And they are non-trees for different reason. In the first case, it's a cycle. In the last case, it's disconnected. Right, so both the conditions we need for a tree, which is true in second and third, but they happen to be isomorphic. So another way to define a tree, very different way, is that if you look at paths from vertex V to U, how many will you see? Can there be 2 paths? Sorry? Right, so one key property is that any 2 vertices have a unique path. Why is it important that there will be a path? Because we have assumed connectedness, right? So again, these 2 axioms of the tree give you this fact that this property of a tree, that any pair of vertices, there is a, first of all, there is a, has to be a path, and then it has to be unique. This can be taken as another definition. So we can actually prove this equivalence. So graph G is a tree if and only if for all vertices UV there is a unique path. So how do you show this? Easy case is the forward direction. If G is a tree, then by the axioms there is a path, and 2 paths would give you a cycle. But yeah, formally proof is a bit longer than the basic idea. So let G be a tree. And for the sake of contradiction, assume 2 paths between some vertices U and V. Okay, take two different paths and using, so now from these two paths we will get a contradiction. That's the goal, prove by contradiction. So first is path P, which is in x vertices, so x0 to x1, x2, and let's say k length goes to v. Second is P prime, goes from u to v via y vertices. And some other length can be anything, right? Let's say k prime. So you have u, v, this path P, and the other path P prime. Yeah, so it seems obvious that there has to be a cycle. How do you formalize this? Yes, so we basically want to use this lemma. We want to create a walk from x0 to itself without using two consecutive same edges. Then we can, assuming that you have proved this formally, this will give you a cycle somewhere in the graph. So, so the tricky condition is this two consecutive edges should be different, right? That can we claim that if we just start from u and end in u using this P composed with P prime? Yeah, we cannot guarantee that because maybe the first edges of P respectively P prime, they are the same. So then the walk will have the same edge, right? So, sorry? P itself will be a path. It has nothing to do with P prime. So what we have to do is we have to identify, that's the complication, and the proof becomes longer. You have to identify a location in P where the first time you see a difference with P prime. So let's say that first location is xi plus 1. And in here the first location is yi plus 1. Okay, so basically u to xi plus 1 and u to yi plus 1 in the respective paths, they look the same. And they differ at this I plus 1th place. And similarly, you want to avoid in the walk edges incident on V. They may be the same, right? So you want to get to a differentiator, which let's say is j minus 1. So intuition is one thing, but these are the places in the proof where you will always make mistakes because you will assume too much. Okay, you have to carefully divide into these cases and then apply a correct property. So, okay, let's write that down. So this least I such that xi plus 1 is different from yi plus 1, and largest j I think j also I need the least, right? Sorry? G will be I plus 2. Yeah, no, so we want J to be the, yeah, last, which means the largest, I guess. Yeah, let's see, max J where, what is the question? So you want, I mean, you are taking the walk from U to V, although this is an undirected graph, but the walk we are seeing as walking in order. So the first place where you see a difference, that's I plus 1, and then you will reach V, but you go back and see where is the first place where you see a difference, that is J minus 1. So J minus 1 is the largest, J is the max, and I is the min. Is that fine? Okay. You are saying that J minus 1 can be smaller than I plus 1? Then? Why do we care? As long as I and J exist, we are fine. Min I and max J. Sorry? Okay, but what is the, no, but are you saying that I and J don't exist? What are you saying then? If they exist, so I have defined them. That is true, yeah. Let us not make it that complicated. Let us just assume that they are equal. We will handle it in the end separately. Without loss of generality, equal length. Yeah, say we take the simple case where the lengths are the same, and then look at min I and max J. Is that fine? We'll handle the unequal length in the end once this is done. Okay, so now I think wait, what are you saying? In this case, what is U and V? What is U and V in this case? Okay. Then? Well, min I is then just here, the first edge. And the max J is here. What is the problem? The path wouldn't, there is no path. We want to construct a walk. So there will be a walk. I mean, I haven't even defined the walk yet. So let's define the walk, assuming these ij. So consider the walk I want to go from xi to xj. And then at xj, I can switch to y's. This is what we have assumed, right? That j is max. So if you take instead of j minus 1, if you take j, then at that place you have the same thing. So you come up to xj, and then from there you switch to the y. So you switch from path p to p prime. And then you can traverse on the y's backwards. So y j minus 1 to yi. Right, and what is yi? Yi is the same as xi. Okay, so this is the walk I intend to do. What was the problem in this? No, but somebody was saying that this ij will not work. Okay. Okay, so now we have a walk where we have removed this only issue in invoking the lemma of consecutive edges being same. Now consecutive edges can't be the same. Is that clear? Because the only possibility of consecutive edges being same is then within the path p and within p prime, but within a path that cannot happen. Okay, so we are using separately the properties of p respectively p prime, but we can see it in a walk now because we have removed the overlapping vertices in the beginning and in the end. So this, it has, yes. X of j minus 2. Xj minus 2, then xj, j minus 1, and then yj minus 1. No, but what are the consecutive edges? What is the possibility for consecutive edges? So you have to look at j minus 2, j minus 1, and xj. These two edges have to be the same. Can they be? Well, they are in the x's. Inside the path, it cannot happen. It can only happen when you switch from x to y, so those things are automatically ruled out. So it has no consecutive edges the same. So this is because of PP prime are paths. Okay, that was the only thing why we had to do all this jugglery. So at this point, we can now invoke the lemma and go from walk to a cycle. But remember that the cycle may not be using xi. In the general proof, it just shows that there is some cycle, may or may not be xi. Yes? No, it may not be, because that was the example somebody gave. You should talk to your friends. So it was something like yeah, you can go from x0 to something, and then there is a cycle. Let's say at x1. So it's not that x0, x1 is appearing consecutively. You take x0, x1, you do the cycle, then you take x1, x0. Is that fine? That's the picture. So these weird examples can happen. That's why these graph proofs can be very tricky. You think you know everything, but there is always something missing when you write the proof. Okay, so yeah, so now we invoke that lemma, and it gives you a cycle. Cycle in G, which is a contradiction. There exists a cycle in G, which means that the contradiction means that there cannot be P and P prime, there is only P. Okay, so this gives you from tree you get a unique path for all pairs of vertices. Now the converse. So assume that for all uv the path is unique. And from this you want to deduce what? That G is a tree, which means that G has to be connected. Is that clear? Connectedness is clear because the path is not only 0, 1, but it's always 1. There is always a path. So G is a connected graph. Second thing you have to show, more importantly, is that there is no cycle. It's G is cycle free. So suppose there is a cycle. For the sake of contradiction. So it is x0 to x1 to x0 to xk, which is x0. And now what will contradict the unique path assumption? Yeah, so let's see that. So x0 to x1, and then there is this path to xk minus 1, then an edge. So this x0 to x1 edge, this clearly is a path from x0 to x1 vertices, but there is another way to go from x0 to x1, right? You use the cycle in the reverse. I mean, you use the bottom path in the reverse. So I draw these arrows, but actually these are not arrows. This is just connections. So you can, okay, let's change this color. Can go from here and then take this, right? So there is an orange path and there is a red path from x0 to x1. So that is the contradiction. x0 to x1 has two distinct paths. Which is a contradiction. Is this clear? Just the first edge itself gives you the contradiction. Okay, so the contradiction means that all paths are unique. And hence G is a cycle. A G is a tree. Right, so we have shown both sides. So then we have a independent definition of a tree. You can talk in terms of unique paths. And the original definition of tree was via connectedness and cycle freeness. You can use any of these now. Going back to this equal length, yeah. No, what change you want here? Say that again. On previous slide, okay. Y I plus 1. In what case? No, are you talking about the unequal length case? Or no, I mean, again, why can't I just write what I have written? Find the min I. I am not assuming anything. I am just saying that pick the min I. If it exists, I am fine. So the question is, again, this I and J, do they exist or not? Is there anybody here who says that they may not exist? I mean, it's simply an array. You just keep building the sub-array of P and sub-array of P prime. Somewhere they will differ. So 2 and 2 prime. What is the problem? Just have to compare the two arrays. Compare the two arrays from the beginning and from the end, respectively. What do you do when these arrays are unequal length? No, for the unequal length, I would simply say what somebody was saying, that from the starting array, you will find the I as here, and from the end, you just go to an equal length, which is in edges incident on V, compare them, then the ones behind them, then the ones behind them. So it won't matter. It will be again similar thing. In one case, you compare your distance from U. In the other case, you compare your distance from V. Is that fine? So all cases are covered. Hence this is without loss of generality. Okay. So in that case, your xi plus 1 will be V, you are saying. There will be no I plus 1, j minus 1. Yeah, so that case you can treat separately, can't you? So basically we want I and j to be separated enough, j minus I greater than equal to 2. we want enough, I think the only case remaining is this single edge case, when path length is exactly 1, but that you can handle separately. As soon as you have 2 edges in the path, should be fine, whatever we have written. Okay, so I hope this answers all questions. So let's now develop more properties of a tree out of this. So what happens if you remove an edge in a tree? Sorry? Is it a tree? A tree minus an edge, is it a tree? So can you say more about what remains? So in a tree, every edge is actually a unique bridge. So if you cut it, then you get 2 connected components. There is no way to go from one to the other. That's the property coming from unique path. So this from a tree, removing an edge UV basically disconnects U and V. So that's the only bridge available. Okay, so in particular, what can you say about the number of connected components? Is it 1, 2, 3 or more? No, yeah, in a tree it is 1, it's connected, but now when you remove edge U comma V, what happens? Yeah, then the connected components grow from 1 to exactly 2. So the first is the connected component of U, the other is the connected component of V, and there is no way to go from one to the other. How do you prove this? So let G prime be this tree minus the edge, and suppose that there is a path in it. So what happens? Yeah, so previously you had this edge U to V in the graph G, and after deleting it, still you have something surviving. Some path goes from U to V, right? So this, so now from G prime, in G prime, if you add an edge, the edge that you had deleted, if you add it back, then you get the original tree with non-unique paths. So in G, this U to V path is then not unique, right? Which can't happen because G we assume to be a tree, and so this means that in G prime there does not exist a path from U to V. Is that clear? Now, what about the other connections? So connections of U to W and V to W prime that existed before in the graph. What happens to them if you remove the edge UV? Uh, yes, but if you look at the vertices W that are connected to U without using the missing edge, they remain connected, and symmetrically for V, right? So you get two connected components. And G prime has two connected components. So this is the connected component, first connected component, this is the second connected component. Okay, the connections of U without needing edge UV, and the same thing with V. Okay, what can you say about these connected components? Yeah, they are subtrees. Let's write it here then. Each is a tree. Is this clear? What would happen if you remove two edges from a tree? Yeah, so now you can just induct on this proof, and you can see how this will change. Because the first edge you remove, this picture appears. The second edge that you remove, now it has to be in one of these subtrees. So there again you can apply induction. So you will get three connected components, and each is a tree. Okay, there is a more, there is a different kind of interesting property, which is that what can you say about the degree of the vertices in a tree? Sorry? At most 2. No, you are being too optimistic. See, these things are also called trees. Can be anything. So what property can you expect from degree somewhere in a tree? Not everywhere. Everywhere you cannot say, because degree can be arbitrary. Yeah, those are more complicated properties. The simplest property is that there is a vertex with degree 1. So a finite tree, and in discrete math we will only study finite trees. So a finite tree has a degree 1 vertex. How do you prove this? Sorry? Assume there is a vertex. No, so by connectedness there is no isolated vertex, so all the degrees are at least 1. The question is, there is a vertex with degree exactly 1. How do you show that? You mean you are assuming every vertex has degree at least 2? Right, yeah, so you have to give a proof of that type. So the idea here is, I mean, you basically have to use finiteness, right? If you don't have, if you look at an infinite tree, can you give an example where there is no vertex of degree 1? Every vertex has degree high. Exactly, right? So infinity is a problem here. But if you want a finite tree, then there has to be degree 1. So you use this finiteness assumption. So each vertex, or let me just say degree greater than equal to 2 in a vertex allows to create an infinite walk. Well, tree, right? Tree has no cycle. So what you do is you pick any vertex. Clearly, it will have degree at least 1. It's a connected graph. It's a tree. So there will be a neighbor. So you go to the neighbor, and the principle you or the invariant you follow is when you enter a vertex by an edge, you exit the vertex by a different edge. Yes. Sure. But how do you get degree 1 vertex from that? Well, I mean, it can, yeah, it has to end somewhere, but why should that somewhere be degree 1? It's not so simple. No, you have to think of this algorithmically. So you actually try to develop the walk incrementally, and in every step, you ensure that when you enter a vertex, you exit by a different edge. So if you are entering vertex V, then take a different edge, and this is just this is how you will develop the path. So these two edges, you keep them different. Okay, so this is what degree 2 or more allows, that wherever you will reach, you will exit by a different edge. And is that enough to show that you will need infinitely many vertices? Yeah, so that is where you will also invoke cycles finally. So this creates an infinite walk which can't have a cycle, as this as we are in a tree. Okay, so this absence of cycle and taking a different edge whenever you reach a vertex to exit, this will actually keep on then growing, I mean, ad infinitum, you will get an infinite walk. Okay, so yeah, this means that somewhere it has to stop. And that means that there exists a vertex of degree 1.